Thank you. Okay. All right. Hi again, everyone. Same name. My name didn't change, don't worry. I'm Adeline, and I'm going to walk you through my world of chemistry, computers, and the environment. So as I was saying, I am finishing my PhD here in Luxembourg, and my research falls in the middle of these three fields: chemistry, informatics, which is basically computers, and environmental science. That blue dot, that's where I work. And to begin to explain to you how I got there, I first need to tell you a little bit about chemistry, because that's what I studied before I started my PhD. So when you tell people you're a chemist, they think they look like Jemp, they think they look like this, they think they work in a place like this, or if you're a wizard at Hogwarts, a place like this, which actually is not so bad. But I don't. I actually work at a computer all day long. Oh, no, I love it. No, guys, I love it. I love writing code, okay? I love writing code. I love programming. I love working with computers. I think computers are the best thing since sliced bread. And here are the top 3 reasons why. 3 reasons why. First reason, computers are dumb. And when I say dumb, I mean they do everything you tell them to do, right? And oftentimes in research, sometimes you even get wrong or unexpected or weird results, but it's all because the computer did exactly what you told it to do. And actually, this turns out to be a very powerful thing. Second reason, computers are smart. And I know this might seem a bit contradictory, but it's true, right? Computers are really good at finding patterns. They can do this really quickly, and most of the time, maybe all the time, without any errors. Last reason, computers are very hardworking. They're very good at huge, repetitive, boring tasks, right? No more manual work, guys. It's the power of automation. You know, anything you have to do over and over again, let the computer do it. So the question is then, how can we marry these two fields? How can we work with computers and take advantage of all these features and work with chemistry? To answer that question, we need to first consider, how do we computationally represent a chemical? How do we take a chemical as we know it, you know, this physical entity in the physical world, and translate that into the computer world in a way that computers can read and understand a chemical? The answer is that there are many ways to do this. And for me to best explain this to you, I'm going to tell you that there are just many ways, or many names of this for the same thing. Let's first consider the apple. And since we're in Luxembourg, I'm sure all of us in this room know at least 5 different ways of saying apple, right? Let's hear it. Apple. Oh, apple. Apple. Okay, I think I heard 6. Good. But here we go. At least 5 different ways of saying the same thing. Apple. Now, in the same way, chemicals or chemistry in the computer world have many different ways of saying the same thing. So here I show the molecule caffeine, the one we know and love. Possibly abuse, but okay. And what we see is that caffeine has many different names, right? It has many different, what we call, representations. And each representation I show here can be read and understood by a computer. But then you might be thinking, why so many? Why? What's the point? And I'm going to let you in on a little secret. And if it's one thing I want you to remember when you walk out of this auditorium, it's this: no chemical representation is perfect. And if you think about it, it kind of makes sense, right? You know, you're taking this physical thing, a chemical, and you're translating it into an abstract, intangible concept for a computer to understand and read. And the thing is, there are many ways to do this, as I said. And each different way, could be suited for different things. To think about it this way, it's the same thing as saying, you know, there's no such thing as a perfect outfit, right? You need different clothes for different activities. You're not going to go to the beach in your space suit, right? You're going to go in your beach clothes. Ever wonder why superheroes have superhero costumes? Black Panther ain't saving Wakanda in pajamas. Am I right? So just in the same way, different representations for different uses or different problems that we're trying to solve. Now comes the tricky part. What problems are we trying to solve with chemistries and computers? I'm sorry to tell you, but actually we do have a bit of a problem, and it's that there are chemicals in our environment that should not be there. Environmental chemical pollution is a problem, and let's remember for a second that the environment is not, beautiful lakes and mountains and oceans and nature which is just out there, right? Environments also include things like our homes, our schools, our offices. This auditorium is an environment as well. Who brushed their teeth this morning? Good, good. You all used a form of chemical, right? A chemical product. And the fact is there are over 350,000 chemicals being produced and used around the world. 350,000, more than 350,000. And they come in all shapes and all forms, right? We either use them directly or sometimes even indirectly. And when I'm talking about chemicals here, let's just focus on those that are man-made for now, the synthetic stuff. Stuff like cleaning agents, your detergents. Drugs are considered chemicals, right? Toothpaste, which I hope everyone used. Things like pesticides, things like engine oil. Name it, it's probably containing a chemical or is a chemical product. We are so exposed to chemicals that it's even been found in the hair of our kids. This study came out very recently. But not just that, it's also in the rainwater, right? And it's at levels so high that we're being told, don't drink it. Remember our old friend caffeine? We all know caffeine is in things like coffee and tea, but in a place like Luxembourg and actually many other places, it's considered a drug because it's a stimulant, right? And in a study we conducted of various Luxembourgish surface waters, so we collected samples from rivers, we found that caffeine, out of about 90 pharmaceuticals we tested, had the highest concentrations throughout. How much was there? It doesn't sound like much, right? You'd need to actually drink quite a bit of water, so quite a bit of this river water, 300,000 liters of water just to get the amount of caffeine you'd get in 1 cup of coffee. Doesn't sound like much, right? Is it? Maybe it's not for a human adult, but what about a child? What about a baby? What about fish or grass or frogs or all the little organisms that live in the water and are constantly being exposed to caffeine? Will it affect them? Is it toxic? And, how did that caffeine even get there in the first place, right? Are people just pouring coffee into the rivers now? And what's going to happen to this caffeine in 2 weeks, 2 months, 2 years? Is it still going to be there? These are all urgent questions on chemicals in the environment that our research, my research, tries to answer. And I got to tell you, this is a real big challenge. It's really, really tough. But luckily, when you have tough challenges, you also have good friends. And if you remember that dumb, smart, hardworking friend, it's the computer. Computers can give us some urgent answers to chemicals in the environment, right? We can use things like databases. We can use things like algorithms. We can try to build models to predict what happens to these chemicals. We can build data pipelines and help us with our analytics. And this is where I work. Chemistry meeting computers, meeting environmental science. And remember how I talked about those different chemical representations? Each representation is better suited to different tasks. For example, you would not necessarily use the same representation when you have a chemical database compared to when you want to build a model. This is something to keep in mind. Another thing to keep in mind, it's not just caffeine. We detected many other Thank you. We detected many other pharmaceuticals in Luxembourgish waters. This is just a couple of them. And as we know, pharmaceuticals are not the only chemicals we use, right? What about pesticides, flame retardants, detergents, cosmetics, all the hundreds, maybe even thousands? Do we ask ourselves what happens to them when we produce and use them? So we do have an environmental chemical pollution problem. But what I want to share with you is that maybe we have some solutions. And I believe that big problems like this need interdisciplinary solutions. And interdisciplinary solutions need people like you. We don't just need chemists or computer scientists. We need all kinds of people with all kinds of expertise on the same team, because the problem of environmental pollution is very complex. It's very big, and we need all kinds of people, lawyers, investors, artists, activists. We need you, and I hope you'll join the team. Thank you very much.